All right, so the end of lecture 7a was kind of abstract. We will be doing some examples. So hang on here. So we emphasized at the end of lecture 7a that there's another kind of subgroup that's important, the centralizer of any given element. It is a subgroup of G. I'm not going to prove that it's a subgroup. That's something you should be able to verify. Again, a proof difficulty level that could show up on the exam. Here's a few more facts that are of a difficulty level that could show up on the test. If H and K are subgroups of G, then their intersection is a subgroup of G. And this fact generalizes to the intersection of an arbitrary number of subgroups of G. So you can write these two implications. Let's just, I won't write out the proof, but let's just briefly imagine writing out the proof, say of the first one, just to keep things simple. You could use the one-step or two-step subgroup test, right? That's what we have, the tools we have. There's the finite subgroup test as well, but that doesn't apply here because this is a general fact that evidently applies even if G is an infinite group, a group of infinite order. So if H and K are subgroups of G, then their intersection should be a subgroup of G, is the thing you would be trying to prove. Could you do it fairly easily, say with the one-step subgroup test? Yeah, it's not too hard. Let's just think about it here. Say you had two elements in the intersection, A and B. You would need to verify, though, again, first that the intersection is non-empty, but since H and K are subgroups, they have at least the identity element in them, and therefore the intersection has at least the identity. So you can verify that first. If you were given A and B in the intersection, is this product in the intersection might seem difficult at first glance. How in the world am I going to deal with that product? But it's not that hard, actually, because of your assumptions. Don't forget to use your assumption. You're assuming H and K are both subgroups of G. So A, B inverse is going to be in both H and K automatically because you're assuming H and K are subgroups. You're basically done. It's a pretty easy proof. Maybe easier than I should put on the test. It's in both of them, so it's in their intersection. It's in both H and K because you're assuming they're both subgroups. Use your assumptions. Maybe I put it on the test. If you were doing the more general fact, you would just need to emphasize that if A and B are in the intersection of all these H alphas, that they are in all of them. For each alpha in, what's this thing? Capital omega, where does that come from? That's just an arbitrary set here. Don't worry about what capital omega is. Just an arbitrary index set for the intersection. Could be a finite set. Could be positive integers. Okay. Don't worry about what that is. Just say if an element's in the intersection of these H alphas, then it is an H alpha for every alpha in capital omega. Emphasis on the for every. And it's really not that much harder. Let's just see that. I want to quickly go over the next slide, even though it's kind of complicated. We'll come back to it. Given an arbitrary, given a group G and an arbitrary subset of G, then the notation where you put pointy brackets around the subset, that's not an element, that's a subset. Not necessarily a subgroup, so I'm only using the set inclusion here. S is not necessarily a subgroup. It's a subset. This notation does represent a subgroup, though. It's defined to be the smallest subgroup of G containing S. And I probably should put the of G in there, just for extra clarity. Of G. does that mean? It means, first of all, that subgroup contains S, meaning S is a subset of it. Not a subgroup. S is not necessarily a subgroup. And it also means, if you got some other subgroup of G that contains S, then in fact this thing must be inside that. And I could have written this, and I did. Over there. It's the smallest subgroup of G containing the set S. This would be the subgroup generated by S, you might say. And if S happened to have two elements, for example, if S consisted of two elements, A and B, then you could also write this as this. And that, with the linear algebra analogy, is analogous to a subspace of dimension 2. A subspace spanned by two vectors, at least if those vectors are linearly independent, it would be dimension 2. If they were not linearly independent, it would still be one-dimensional subspace. Okay, that's the analogy here. This is similar to the idea of a two-dimensional subspace of a vector space, at least when those vectors are linearly independent. And then you could generalize it. If S had three elements, it would be generated, the subgroup generated by those three elements would be analogous to a subspace of dimension 3 in linear algebra, at least if the vectors were linearly independent. As an example, say G is positive integers under the usual operation of addition. And maybe A is the number 6 and B is 8. What's the subgroup generated by 6 and 8? Meaning, what is the smallest subgroup of Z containing both 6 and 8? If you think about it carefully, I'm not going to prove this. It would consist of all multiples of 2. The GCD of 6 and 8. The group operation is addition. Which, interestingly, is the same as the cyclic subgroup generated by 2. In general, this kind of thing is not going to be cyclic. In general, if you've got two elements in there. But in this example, this is cyclic. It's generated by one element as well. By the way, the notation is consistent. This is the smallest subgroup of Z containing 2 as well. The notation here. And the idea of the smallest subgroup containing the set does work in the situation where we're talking about a cyclic subgroup. Does that make sense? It's not a proof, but hopefully it makes intuitive sense. This is the smallest subgroup of Z that's going to contain both 6 and 8. It also happens to be the smallest subgroup of Z containing 2. It also turns out that this smallest subgroup of G containing S can be thought of as the intersection of all the subgroups of G that contain S. It's an artifact of the fact that it's the smallest subgroup of G containing S. Another proposition, and this is harder to prove, is that you can represent the smallest subgroup containing S as the product of all powers of elements of S, essentially. Where these SI don't have to be distinct. SM could be the same as S1, for example. That's harder to prove. And that's got a linear algebra analogy as well. This is analogous to the concept of span of a collection of vectors. Instead of taking a linear combination of an arbitrary collection of vectors, we have an arbitrary product power combination, you might call it. We're not going to make a big deal of this, but it's useful to realize sometimes. All right, for our remaining time, what we're going to do is we're going to look at some questions we might ask about cyclic groups and consider examples of cyclic groups and start working toward trying to maybe answer these questions empirically, meaning based on our experience, sort of like experiments with cyclic groups. We'll probably do that again a lot on Friday as well. Take our examples, see if we can come up with propositions based on those examples. And by the way, the propositions are going to be the same as the theorems you will read about in Chapter 4. You really should have skimmed over them at least by now. Will we do any proofs on Friday? I'm not sure. Maybe, maybe not. We're just going to try to gather evidence, get good at calculations with cyclic groups, and gather evidence for observations that we make to try to answer these questions. Okay? And I think it's important to get good at the calculations first and develop an intuitive feel for what's going on with cyclic groups before we try to prove things. Remind you quickly, a group is cyclic if there's an element A that generates the group. The cyclic subgroup of G generated by A equals G. That means G itself is cyclic. You get what I'm saying there? Subtle distinction here. The cyclic subgroup generated by A and G being itself a cyclic group. If there's some element A where the cyclic subgroup generated by A actually equals the entire group, then you say the entire group is a cyclic group. A is called the generator of the cyclic group, and we can give examples. And the most important examples are Z and Zn. Z is generated by 1. It's also generated by -1. Group operation being addition. You aren't talking about powers of 1 there. You're talking about multiples of 1 when the group operation is addition. The set of all integer multiples of 1. For example, when I write 3 times 1, I'm not saying the operation in Z is multiplication. Careful. I'm not saying the operation in Z is multiplication, even though I do know how to multiply these things to get 3. I'm saying 3 times 1 means 1 added to itself 3 times to get 3. When I write -1 times 1 or just -1, I mean the additive inverse of 1. And when I write -3 times 1, what I really mean is add the additive inverse of 1 to itself 3 times. -1 plus -1 plus -1, which gives you the additive inverse of 3. Very subtle things here. That is important to realize, though, because I could have a group whose operation is addition, and it doesn't make sense to say multiply n times G in the group. It just means if n is a positive integer, it means add G to itself n times. I'm not saying the group operation is multiplication. But this definitely gives you every integer. 1 and -1 are both generators. And there are no other generators of Z. Those are the only 2. Zn is a cyclic group. 1 is a generator, for example. And so on is in fact n minus 1. That's always a generator. Are there other generators? There could be, there might not be. Z4 is an example where there are exactly 2 generators, or 1 and 3. 2 is not a generator because the cyclic subgroup generated by 2 is not the entire group. It's just 0 and 2. But in Z5, contrast this here, in Z5, it turns out that every non-zero element is a generator. 1, 2, 3, and 4 are all generators in Z5. For example, thinking about the cyclic subgroup generated by 2, and just imagining doing the repeated addition. Go ahead and write it out here. Doing addition mod 5, I get 2, then 4, then 6 mod 5 is 1, then 8 mod 5 is 3, then 10 mod 5 is back to 0. I do get the entire group Z5. 2 is a generator of Z5 under addition mod 5. You can do the same verification for any of those other elements. 0 is not a generator, it's the identity. Cyclic subgroup generated by 0 is just 0 itself. And it's always true for the identity. Okay, so sometimes you might only have 1 and n minus 1 as generators, sometimes there could be more. But these two will always be generators of Zn. It may or may not be more. What about the UNs? Are those cyclic groups? We've actually already considered enough examples that you should know the answer, at least if you're really paying attention and thinking carefully. Are the UNs always cyclic? Group of units under multiplication mod n. They're not always cyclic. Sometimes they are, sometimes they're not. It depends on what n is. U8, 1, 3, 5, and 7, does that have a generator? It will not have a generator if all these elements are their own inverses. 3 times 3 is 9, mod 8 is 1, 3 is its own inverse. 5 times 5 is 25, mod 8 is 1, 5 is its own inverse. 7 times 7 is 49, mod 8 is also 1, 7 is also its own inverse. This is not cyclic. None of these cyclic subgroups that are generated by these different elements give you the entire group. They all give you subgroups of the whole group, but they do not equal the whole group. So U8 itself is not cyclic. What about U10? I probably shouldn't erase that so fast. Sorry. Positive integers less than 10 that are relatively prime to 10 are 1, 3, 7, and 9. What's the cyclic subgroup generated by 3 under multiplication mod 10? 3 times 3 is not 1, it's 9. This has a chance. Three cubed is 27, mod 10 is 7. 3 to the 4th is 81, mod 10 is 1. This does equal U10. U10 is cyclic. Does it have any other generators? What's the cyclic subgroup generated by 9? 9 squared is 81, mod 10 is 1. This does not equal U10. That's okay, I only need to have one generator to be cyclic. Is 7 a generator? 7 squared is 49, mod 10 is 9, not 1, this has a chance. 7 cubed, let's do that as 7 squared times 7, 9 times 7, mod 10. 63 mod 10 is 3. Right, you see what I did there? Mod anytime you want, as I've been talking about recently. I went ahead and replaced 7 squared with 9 instead of 49. And then 7 to the 4th, I can do as 7 cubed times 7. 7 cubed is 3. Mod 10. 3 times 7 is 1. 21, which is 1 mod 10. So 7 is also a generator of U10. Here are some important questions to try to answer about cyclic groups. If we know the order of the cyclic group, how many elements it has, 4, for example, 5, 6, 7, whatever, is the number of generators completely determined? We have just seen with U10, which is cyclic, it's got 4 elements, and it's got 2 generators, 3 and 7. We also saw with Z4, just 5 to 10 minutes ago, Z4 was generated by 1 and 3. That's a cyclic group with 4 elements. The order is 4. It's got 2 generators. Do all cyclic groups with 4 elements have 2 generators? Maybe we can verify that in the abstract. Think about an arbitrary group, cyclic group of order 4, which would be generated by an element of order 4, given some group G and some element A in G with, say, order 4. The cyclic subgroup generated by that element, so only think about positive powers first here, would consist of A to the first, which is A squared, A cubed, and then A to the 4th equals E. A to the 5th is A to the 4th times A, is E times A, is A. Cyclic cycles here. A to the 6th is A to the 5th times A, which is A times A, which is A squared. Or I could write it as A to the 4th times A squared, E times A squared, which is A squared as well. A to the 7th is A to the 6th times A, which is A squared times A, which is A cubed. A to the 8th is going to be, if you like, if you want to think of it as A to the 4th squared, then it's E squared, which is E. Or you could do A to the 7th times A, which would be A cubed times A, which is also E. Etc. What about negative powers? And the 0 power definitely equals E. And negative powers, well, what would be the inverse of A? A to the 4th equals E, so A times A cubed equals E. So the inverse of A is? A times A cubed equals E. A inverse equals A cubed. And A to the negative 2 could be thought of as either, so I'll write A cubed down here. A to the negative 2 could be thought of as either the inverse of A squared which would be a cubed squared, which would be a to the sixth, which we know is a squared. Or it could be thought of as the inverse of a squared, which is itself, since a to the fourth is the identity. Either way, you get the same answer. That's good. This will equal a squared. A to the negative 3 will equal a. And a to the negative 4 will equal e. A to the negative 5 will be the same as a to the negative 1, which was a cubed. I know I'm putting these all in strange order. They're going to consider the positives first and then the negatives. They're just set, so it doesn't really matter what order I put them in. So this is a finite set. The cyclic subgroup generated by A really is a finite set because I get repetition. How many generators does it have? Does it have 2, like those other ones did? A is a generator. Is a squared a generator? What do you think? Take a guess, without even doing calculations. No, it's not. It's analogous to the fact that in Z4, 2 is not a generator. The cyclic subgroup generated by a squared is going to consist of integer powers of a squared, like a to the fourth, but that's back to e. A to the sixth is back to a squared. I can consider negative powers too. This is a 2-element set, e and a squared. What about the cyclic subgroup generated by a cubed? Again, I could consider negative powers. I'm not going to bother. That's the same as a squared. This is the same as what? A to the ninth. That should be the same as a. Uncycle. A to the fifth is a to the sixth is a squared, a to the seventh is a cubed, a to the eighth is back to e, a to the ninth should be back to a, and it is. This is the entire cyclic group here. In other words, a cubed is a generator too. E is not, of course. So this cyclic group of order 4 again has 2 generators. And essentially, because of the abstraction here, this, you might say, is essentially a proof that all cyclic groups of order 4 have 2 generators. This is an abstract situation, which it is. Now, I didn't write sentences, but essentially that could be the idea of the proof, that every cyclic group of order 4 has 2 generators. And we can find them. They're the original generator and its cube. Or in additive notation, the original generator and 3 times it in Z4, 1 and 3. We could consider other examples. We will on Friday. Can we determine whether 2 powers of a generator result in equal elements or not? In general. Our experience with an abstract group of order 4, cyclic group of order 4, seems to indicate that maybe we can. Let's try a cyclic group of order 5. In the abstract, got an arbitrary power like, say, a to the 73rd power, and Well, okay, I'll put a question mark here to really address this question. Is a to the 73rd equal to, say, a to the 32nd? Could that possibly be true? Its truth or falsity would be equivalent to this being true. Let's put a question mark there. I don't know if those are equal or not yet. Let's see, that would be equivalent by properties of exponents to this thing being true, which now takes 73 minus 32. That would be equivalent to a to the 41st power equaling e. 41 is not a multiple of 5, however. It's one more than a multiple of 5. A to the 41st is going to be the same as a to the 1st in this group, which does not equal. I'm implicitly assuming that well by writing that. So yeah, that kind of question could be answered either with particular examples or in the abstract. If we have a generator, can we find the order of its powers? The answer is yes. How do the orders of the elements of a cyclic group relate to the order of the group? Say you got a cyclic group of order 12. What are the possible orders of subgroups of it? Of elements in it and subgroups? Yeah, and what types of subgroups do cyclic groups have? Not two. Typo there at the end. Okay? So read chapter 4. Chapter 4 does answer all these questions. You can certainly read the proofs. Mostly Friday we will do lots of calculations to try to make these terms propositions and maybe look at some proofs. Certainly next week. See you then.